But this is working, right? Yeah. So I will try to speak loudly. So welcome back to this morning session. I will try to resume or continue what Matteo was discussing about in the previous section. And I will discuss again about density functional beyond standard LDA or GGA. And in particular, I will try to introduce a general framework for the development of advanced functional, which is called the adiabatic connection formula. And then I will briefly, with some extent, discuss hybrid functional and van der Waals interaction in density functional theory. And then, if I will have time, I will briefly address these really advanced functional random phase approximation and something beyond random phase approximation. But just let me start with a very brief introduction, since this you already saw many times yesterday and this morning. Also Matteo explained very well. This is some remark on density functional theory. We know it's an exact theory for the ground state of any many-body interacting system. And the conceptual advantages of density functional theory is to shift the perspective from a many-body perspective, so many-body wave function, to the electron density, which is an object that depends only on 3 or spatial coordinate, while the many-body wave function is an object that depends on 3n if coordinate if n is the number of your electron. But besides this conceptual appealing of DFT, the real strength of the theory, especially in the Colonna formulation of density functional theory, is its very good price-performance ratio, I would say. And this is thanks to the Colonna mapping, essentially, so that you can compute ground state property of any interacting system simply solving a set of self-consistently a set of single particle Schrödinger equation. And the central quantity, as already said many times during this talk, is the exchange and correlation energy function. The real advantages of Colonna DFT is that treating exactly the non-interacting kinetic energy and the R3 energy, what is left outside, the exchange and correlation energy, is usually very well approximated with some local or semi-local approximation based on essentially property of the homogeneous electron gas. And as I said, these LDA and GGAs, as I will just briefly comment in the following, they are usually very good approximation in many applications, but still there are some situations in which they qualitatively fail. So not only quantitative, but also qualitatively failure. So this is just a reminder what is the local density approximation. The idea is that the energy density of any homogeneous system in a given point of the space is approximated by the energy density of an homogeneous electron gas that has a density equal to the density of our inhomogeneous system in position r. So in formula, this becomes this expression here. It's an integral over the whole space, the density of the system, and the energy density of the homogeneous electron gas. So the exchange energy of the energy density of the homogeneous electron gas can be computed analytically, and it's given by this expression where Rs it's related to the density through this formula. Essentially is the radius of the sphere that on average contain 1 electron in the system. It's just an alternative way of instead of using the density, usually we use this dimensionless parameter Rs. And the exchange energy is analytic, while the correlation energy is cannot be computed analytically. Actually, there are in the limit for Rs that go into 0 with some perturbation technique, one can compute analytically how the exchange energy of the homogeneous electron gas behave, and is given by this second line here. This is essentially a result from RPA calculation, while for value of Rs greater than 1, usually what it's done is that we take accurate quantum Monte Carlo calculation and we feed them with some analytic formula. At the end, what is implemented in all DFT code is a formula like this. There are different parameterization, but actually they are all made on quantum Monte Carlo calculation by Seberly and Alder, or some even recent, more recent calculation. So this is the LDA. The next step beyond local density approximation is the generalized gradient approximation, in which one take into account not only information about the local density, but also about its gradient. And this is usually written in this way as a product of the exchange energy of the homogeneous electron gas times a dimensionless enhancement factor that depends on the local density and its gradient. While for LDA there were only, let's say, different parameterization, but the data for the fit were from one calculation, quantum Monte Carlo calculation. For the generalized gradient approximation, we have more than one recipe, if you want, depending on the choice of this function. Here I just take this picture from the Richard Martin book just to highlight this. And essentially what happens is that all the generalized gradient approximation starts with the same dependence on this reduced density gradient, that is essentially the gradient of the density. And this is because there is an analytic expansion for this close to S equal to 0. So all the generalized gradient approximation starts with this analytic dependence, but then they have different behavior for large value of S, and this depends on the different physical condition one wants to impose to this function. This is not very relevant here, but I just want to say that mainly the biggest part of any interesting system and interesting physics happen with very small gradient of the density. So this explains why almost all generalized gradient approximation improve in the same way on LDA. Yeah, and as I was saying, there are different recipes, and in the literature you can find many other forms of this generalized gradient approximation. So here it's just a slide to comment about the performance of LDA and GGA for small molecule. Here, what I just take number from references in the literature, in which I plot just the binding energy of this small molecule, and I compare with the experiment calculation from local density approximation and PBE. And if you take the average of a big set of this molecule, you can find that the mean absolute error on the binding energy in local density approximation is more than 1 electron volt. If we apply some generalized gradient approximation in this particular case, it's the PBE generalized gradient approximation, we greatly reduce the mean absolute error. Well, almost of 1 order of magnitude. Still, this is usually not enough, at least for chemists, because they usually want to reach what is called the chemical accuracy, which is an accuracy of the order of 1 kilocard per mole, that is more or less 0.05 electron volt. So still 1 order of magnitude less than this accuracy. But still, this performance is remarkably. So already going from LDA to PBE, we really gain a lot in accuracy, at least for binding energy of small molecule. Small molecule, but also extended system, and here I decide to just focus on structural property of bulk system. Here I take just few examples containing metals or insulating system or a semiconductor. On average, what happens is that usually LDA tends to overbind, and this means that the lattice constant are usually underestimated, and the bulk modulus, which is, let's say, the second derivative of the total energy close to the minimum, they are usually overestimated. And this is a well-known drawback of local density approximation. If we add some generalized gradient correction, also in this case with PB, we see that GGA tends to correct this LDA deficiency, but somehow overcorrect it. So in a sense, the generalized gradient approximation tends to underbind, even though the situation is more variable in the sense that we don't see really a clear trend. As a consequence, the equilibrium lattice constant are slightly overestimated, and the bulk modulus is underestimated. Still, I mean, these numbers are very accurate, and usually is what you really need for a qualitative and quantitative analysis of this kind of system. Error of the order of 1–2% is something usually very good. And this to say that, generally speaking, LDA and GGA are quite good approximation. This is the reason why people use a lot of density functional theory with this kind of functional. Still, there are situations in which this approximation, qualitatively fail. And for this kind of failure, one needs to think about some kind of correction. So I just want to list some of these qualitatively failure, starting from the well-known self-interaction error. So when we define or let's say, when we split the total energy functional, and we introduce this R3 term, which is actually the electrostatic interaction, classical electrostatic interaction of the charge density with in itself, we are making an error in the sense that we are letting each electron to interact with itself. And this is, of course, something unphysical. And this is something that, in principle, if we add the exact exchange and correlation functional, has to be completely compensated. So what should happen for one electron system where we have only one electron, this electron does not interact with anything else in the system? The sum of the R3 plus exchange and correlation energy should be exactly identical to 0. And this condition is more or less satisfied by LDA and GGA in most of the situation, but still there are cases in which LDA and GGA badly fail. And one example is the dissociation of the, very simple example is the dissociation of H2+, as Matteo discussed also this morning. And here you see that close to the minimum, we don't see, a big self-interaction error, and the LDA and GGA perform, in this case LDA, perform reasonably well. But as soon as we stretch the system, this self-interaction error becomes more and more relevant, and at the end we find a completely wrong agreement at dissociation. Well, of course, this is not expected since DFT is an exact ground state theory, and one property that you should be able to compute exactly is the ground state density or ground state energy or energy differences. So in principle, this curve should be exactly reproduced if we had the exact DFT, while this is not the case because of this self-interaction error. Another problem that at least can be connected to the self-interaction error is the underestimation of the ionization potential in, here I will discuss molecule, so finite system. There is a well-known theorem that states that the decay of the density far away from the nuclei is related to the ionization potential of the system. And this is true for interacting system and for non-interacting system, so no matter which system we have. But if we had a non-interacting system, this formula really simplifies, since the ionization potential is nothing but the highest occupied, the energy level of the highest occupied molecular orbital. This is simply because we have a single particle picture, the orbitals do not interact, and this is the energy we need to take out one electron from the system. So in DFT, what we have is that this is our real many interacting system, and this is our Colonna system, and we know that the density of the two systems has to be the same, so this means that the ionization potential has to match with the energy of the highest occupied molecular orbital, well, with the minus side. So even though DFT is a ground state theory, here we have a notable exception, since the ionization potential, which, if you want, it's in a sense property of an excited state, is exactly reproduced by exact density functional theory. Of course, this is true if we had the exact functional. What happened with the approximate functional is that this condition is not satisfied anymore, and this can be explained also in terms of self-interaction, in the sense that the Colonna potential far away from the nuclei, because of the self-interaction of the electron with itself, decays exponentially, while it should decay like 1 over r. And this because in the Colonna potential there is also a spurious self-interaction of the electron with itself. And this makes the extraction of electron simpler than it should be in real system. As a consequence, the ionization potential compared to the experimental value is greatly underestimated. Another failure that I will discuss in more detail later is the failure of DFT in dealing with weakly bound system or van der Waals system. Here I show you again an example of the binding energy curve of krypton 2, so the krypton dimer, which is a van der Waals kind of simple dimer, and here I compare the PB and LDA binding energy with the experimental result. Again, here we have a qualitative failure, since the decay of the binding energy when we stretch the molecule is essentially an exponential decay as a function of the inter-atomic distances, while we know that for this kind of simple dimer, the correct decay should be the 1 over r to the power 6. And the reason is that being local in nature, LDA and GGA fail to reproduce these van der Waals interaction that actually are mainly due to fluctuation of the density in one point, induced dipole, for instance, in this case, in another point of the system. So functions that only rely on local property, so local density or local gradient of the density, are not able to give a correct asymptotic behavior for this kind of van der Waals system. In the following, we'll see how to address this in density functional theory. Last but not least, and this is also what Matteo discussed this morning, is the dissociation of molecule in open shell fragment. The simplest situation, the simplest system you may have in mind is the dissociation of hydrogen 2+. What happened here is that if you do a standard PBE calculation, retaining the correct speed symmetry of the wave function, so without breaking artificially any speed symmetry, what you find is that at dissociation, you find an energy which is way too high than the exact result here in black. This is a situation particularly difficult to address with density functional theory or Colonna DFT, because dissociation of the hydrogen 2 molecule, you have, as Matteo explained this morning, two states that are degenerate, and they should be equally well taken into account in your density function. While Colonna it's a single reference Slater determinant, so it's struggle anytime we have multiple determinants that enter in the description of our system. Actually, this very brown behavior can be somehow fixed with a kind of workaround. that is breaking the spin symmetry. And this is the dashed yellow line in this plot. But of course, if we break the spin symmetry and we allow electron to localize, the one on the hydrogen on the left and the other on the hydrogen on the right, we recover the correct, more or less the correct total energy description of the system, but still we have the wrong spin symmetry for the system, because we have an anti-ferromagnetic object, while in reality this is a non-magnetic system. And this is a problem that usually has to do with strong correlation, as Matteo discussed this morning, or in this particular case, this is what the chemists call as static or left and right correlation that is completely missing in standard local or semi-local density function approximation. So just to summarize this first part on LDA and GGA, what I want to highlight is that LDA usually overbinds, so this means that lattice constants are too small and bulk moduli are too big. GGA tends to correct this failure, but somehow overcorrect it. In general, however, the structural, elastic, and vibrational properties are often good enough, especially for the vast majority of systems you may think of. GGA and LDA for most elements predict the correct structure given for a given material. Still, we are far from chemical accuracy. We have some very infamous self-interaction error. We are not able to treat van der Waals interaction, and we have qualitative failure in a strongly correlated system. So how to go beyond this and develop new functional is extremely hard stuff. But one possibility is to start with an exact expression for the exchange and correlation energy and try to make approximation from it. This exact expression is given by the adiabatic connection formula, which I will try to describe here. So the idea is that one can establish a coupling between a non-interacting system, here in this schematic picture described by this lambda equal to 0, with the full interacting system, scaling down the Coulomb interaction. So this coupling is made by introducing a continuous set of fictitious systems in which the electron interacts with the scaled Coulomb interaction. So this W is the Coulomb interaction, and this lambda is a scaling parameter. Moreover, what we ask is that during this coupling constant, we keep the density constant along the path. This can be done through the Hohenberg-Eckert theorem that says that we can always find a local potential beyond lambda to keep the density constant and equal to the real density of our interacting system. So this means that at lambda equal to 1, we have our real system with electron interacting with the right Coulomb interaction, and V of lambda exactly coincides with the external potential, usually the nuclei electron interaction. At lambda equal to 0, since the density is fixed to the real density of our system, we have the Konescham system. So at lambda equal to 0, this term disappears, we have a non-interacting Hamiltonian, and this local potential is just the Konescham potential. In the middle, we have a continuous set of intermediate Hamiltonian. So if you work in this framework, you can go through algebra, very simple algebra, starting with the definition of the total energy for each value of lambda, which is nothing but the expectation value of the Hamiltonian on our ground state wave function for each value of lambda. If we take the derivative with respect to the external parameter lambda, we can use the Hellman-Feynman theorem, and you find this kind of expression. Then once you have the derivative of the energy, you can integrate between 0 and 1, starting from the energy of the Konescham system and integrating this derivative between 0 and 1. And if you do that and you again use the standard decomposition for the total energy as the non-interacting kinetic energy, R3 energy, exchange and correlation plus external energy, you find this final expression here, in which the R3 exchange and correlation energy can be written as a coupling constant, as an integral over the coupling constant lambda of this expectation value of the Coulomb interaction on the many body wave function for each value of lambda we have. So this is a general framework. This is exact in theory. Now we just need to understand what this object is and if we have some tool to approximate it. So first of all, we can rewrite this object. Well, first of all, the exchange and correlation energy is given by our interaction energy minus the R3 energy, which is something that we know how to write it explicitly. And then what you can do is that to introduce this pair correlation function, which is nothing but an object that describes what is the probability to find an electron in R prime once I have another electron in R. So this is an object that should describe really the correlation in our system. So once we fix an electron in R, this object exactly tells us what is the probability to find another electron in position R prime in our system. So it's really a two-body correlation function, so this should really capture all the correlation in our system. Indeed, this is just a rewrite of our interaction energy for each value of lambda in terms of this object. If you integrate this object over lambda between 0 and 1, you got an average pair correlation function, and at the end what you obtain is an expression for the exchange and correlation energy that is identical, let's say, in a formal way to the R3 or Coulomb interaction, but here we have the density and what is called exchange and correlation Hall that is related to our pair correlation function. This function, just describe the depletion of charge density around an electron in R because of exchange and correlation effects. So we know that because of the Pauli principle, we cannot have two electrons in the same position with the same spin, and this is accounted for in this exchange part of the exchange and correlation Hall. And then we have some other more complex correlation effect due to the Coulomb interaction that still avoid two electrons to be close to each other in the in real space. So this object is a mathematical object that describes this kind of physics in our system. So why this expression is important? So this means that if we are able to understand the physical property of this object here, we are somehow able to compute or understand better our exchange and correlation functional and approximation to exchange and correlation function. For instance, what this is very well known and what people discussed, very long ago in the 80s, is that this exchange and correlation Hall is something, it's an object that, of course, depends on the system we are looking at. For instance, here it's the exchange and correlation Hall for the neon atom. And this is how it looks like in real space. We have this very sharp behavior in real space. But what happened is that, and this is so this is the solid line is the real exchange. Actually, this is only the exchange part of the Hall, so only Nx. While here in dashed line is the local density approximation, so the exchange Hall given by the LDA approximation. So if we look at this quantity for the neon atom, you immediately realize that the real one is completely different from the LDA one. So one would expect that then the exchange and correlation energy given by the local density approximation for the neon atom should be completely wrong. But what actually happened is that in the exchange and correlation energy, what enters is only the spherical average of the exchange and correlation Hall. This is due to the fact that the Coulomb interaction depends only on R minus R prime, so you can do a variable substitution, and you can integrate over the angular degrees of freedom. And this is what is done here. So here again, in solid line, we have the spherical average of the exchange for the real neon atom, and in dashed line you have the spherical average of the exchange hole computed with the LDA approximation. And here you immediately realize that they are pretty much the same. They really, and these are for two values of R. So no matter which this R is, they are pretty much the same. This is for the exchange. The correlation is, in any case, an order of magnitude less important than the exchange. But this is just to point out that LDA, although it's an approximation that you would expect to work in a almost homogeneous system, so electron gas or simple metal, this plot explains why it works reasonably well also for non-homogeneous system like an atom, here the neon atom. So, and this is just to show that this expression and I mean, can be really useful to understand successful in this case or failure of any approximation we have for the exchange and correlation energy. Okay, but this adiabatic connection formula can also be used to develop new approximation, as I will show you. And the hybrid function is one kind of approximation that can be understood in terms of this adiabatic coupling integration. So again, let me start from the exchange and correlation energy as an integral over the coupling constant lambda. And if you want, in this plot, I just sketch what is the exchange and correlation energy. It's nothing but the integral of this function of lambda, uxc of lambda, that it looks like this. And in this integral, we have a first part, which is actually the most important one, that is just the exchange energy, and the other part that is the correlation part. So if we look at this expression, and especially at the lambda equals 0 point, so if we take this to be the Kohn-Sham Slater determinant, and we can compute this matrix element explicitly, because this is a single Slater determinant, is exactly what you have in R3-Fock calculation, and at lambda equal to 0, this uxc of lambda equal to 0 is nothing but the, well, sorry, yeah, because you remove the R3. Yeah. It's exactly the exchange, or what is called exchange energy, or R3-Fock exchange energy. So the very starting point of your integration over lambda is this exact exchange energy. So this means that at lambda equal to 0, the exact solution for the system is the R3-Fock solution. Actually, here you have to, I have to point out that these are not R3-Fock wave function, but are Kohn-Sham wave function, because here we are keeping fixed the density. We are not doing really an R3-Fock calculation, but a Kohn-Sham calculation. But the expression of the exchange is exactly the same as the Fock energy in an R3-Fock calculation. Moreover, what is even more interesting in this case is that this expression, like what happened in the R3-Fock theory, exactly cancels the self-interaction error, because this object for I, well, here you have a double summation I and j. For the term I equal to j exactly cancels the self-interaction error you have in the R3 term. So this is appealing also from this point of view, so you are able to somehow remove the error you made in the R3 energy. So starting from this, one can simply say, okay, I know this, I know how to compute it. Let me just do a very crude approximation, and I just assume that my function is a constant, does not depend on lambda, and it's just given by the exchange energy. If we do that, so we completely disregard correlation effect, we have something like R3-Fock theory, but we know that R3-Fock is not really good because, okay, we are completely neglecting correlation effect. But this, we can do something better, and what people realize is that usually LDA and GGA are too negative, close to lambda equal to 0, while they perform in most of the situation reasonably well at full interaction lambda equal to 1. So we can put together these two observations that we have in this point, we know what is the exact solution. In this point, we know that LDA performs reasonably well. What we can do is just do an interpolation between lambda equal to 0 and lambda equal to 1. In lambda equal to 0, we know what is the exact result, is the exchange energy. At lambda equal to 1, we use, again, an approximation derived from the LDA, or generalized gradient approximation. So, and this was the how hybrid functional was firstly introduced by Beck in 1993, and the first scheme based on this linear interpolation is what is called half and half scheme, simply because when you integrate, you got 1/2, the total exchange and correlation energy is 1/2 the Hartree-Fock exchange energy plus 1/2 the exchange and correlation interaction energy. So this scheme, I mean, is not really successful in the sense that on average this does not perform better than LDA or GGA, but after some refinement and putting in some empiricism, if you want, Beck proposed this famous B3, let's say, functional, in which he had mixed exchange and correlation energy from LDA, exchange from Hartree-Fock, and then some gradient correction for the exchange and some gradient correction for the correlation energy. Then, fitting this function on some big set of molecules and looking at thermochemistry, so binding energy and this kind of stuff, he found the best set of parameters to put here. And this is the famous B3-leap functional that is very commonly used by chemists. And this functional proved, at least for small molecule, to be more accurate than standard PBE or local density approximation. And I will show you later some number, let's say. Beck again realized a few years later that actually this expression can be made simpler, assuming some physical intuition that these parameters can be dropped, and they actually are related to the only main parameter, A0. And this is a simplified expression of hybrid function in which we have a general exchange and correlation energy. DFT can be generalized gradient approximation, and again here we are mixing some Hartree-Fock exchange and some DFT exchange. Again, fitting this parameter some thermochemistry dataset, he found some best value depending on which GGA you use here. Actually, I mean, this is quite good, and this performs almost as good as B3-leap with only one parameter. And but still we have some empiricism in it because we have no way to define this parameter, let's say, in a sense, by first principle. But actually this is what Perdue and co-worker did in 1996. They found some argument based on comparison with fourth order perturbation theory on actually how this dependence of lambda should look like. And they suggest not just a linear fit like in the half-half approximation, but a cubic dependence on the lambda parameter. And then again, using exact condition at lambda equals 0 and DFT at lambda equal to 1, they were able to find analytically this parameter, and they suggest to use this value of 1/4, so 0.25%. And this is the famous PBE0 function. The fact that this in a sense, not fitted parameter A0 1/4 is, let's say, more or less close to the parameter that come out from a fit on thermochemistry data. I mean, they are close, so this means that this reasoning is correct, and it's a validation, let's say, of this assumption. So hybrid functional. What's the main ingredient of hybrid function that we don't have in LDA or GGA is the Hartree-Fock energy, which is given by this expression here. We have a double summation over K point and valence band. This is in a crystal. And as you can see, this is no more an explicit function of the density. So this is something that can be defined as an implicit function of the density. So we may think of this wave function as an implicit function of the density. So in principle, in order to bring this hybrid scheme or R3-Fock scheme into the realm of density functional theory, so in a density functional framework, what one should do is to resort to some optimized effective method. So taking the derivative of this energy function with respect to the density and going through a chain rule. And this is quite a cumbersome approach. It's rigorous because then we have a local potential of the exchange, like Hohenberg-Eckert theorem tell us. But it's cumbersome in the sense that in this expression, you see you have to compute this derivative with respect to the wave function that is analytically, in the sense that you have an explicit dependence of the exchange energy on the wave function. And then there are these other two objects. So this one is actually related to the response function of the system, the inverse of the response function of the system. And this one, if you want, is nothing but perturbation theory. So in order to stay in the DFT framework, you have really to do a lot of calculation. These objects are really hard to compute. And actually what instead is done is to stay, in a sense, outside the DFT world, rigorously at least, and to use a direct minimization with respect to the wave function. And this means that what we need to compute is just this derivative of the R3 energy with respect to the wave function. So we just need to compute the effect of the R3-Fock potential on a given wave function. How this is done in plane wave basis set, this is usually done going in Fourier space and then coming back. So usually one take the Fourier, usually one has this object in the code in G space. So what we do, we just use a Fourier transformation and we go in real space. In real space, we compute the product of these two objects. Then we go back to G space to solve the Poisson equation. That is a convolution in real space, so a direct product in reciprocal space. And then we go back to real space and we accumulate over Q point and bands. So as you can see, this is a quite cumbersome calculation, especially because here you have a summation over Q point and balance band. And this is the reason why, as I will show you later, these hybrid functional calculations are really much more expensive than standard LDA or DFT. This is for the exchange potential, but you also need to compute the exchange energy. And again, this is done using this fast Fourier scheme, going in Fourier space and then go back in real space a certain number of times. So in real space, what I want to discuss here is some technical detail, but I think they are really important to understand how this object is computed in the code. So I will try to spend some time on this. So if you take this object and you transform it in real space, you can write it as an integral over the Brillouin zone, and then you have a sum over g vector of this function AQ plus g, which is related to this codensity that I define in the slide, is this object here in G space. So what I want to point out, that this is how the R3-Fock energy is computed in the code, but as you can see here, this denominator is problematic in the sense that it diverges as Q plus G goes to 0. Okay, this is not, anyhow, it's an integrable divergency, so this means that the result of this integral is finite, but since you have this divergency, this means that you have to use a very fine sampling of, in principle, a very fine sampling of the Brillouin zone. And this is something that, I mean, you don't want to do because this would really increase a lot the computational time you need to accurately compute this integral. What is done in in the code is to implement a workaround for this that was firstly introduced by Gigi Baldereschi in 1987, and the idea is very simple, and is to add and subtract to our to the function we have to integrate an analytic function that displays the same divergency. So in a way that when we subtract these two objects, the divergency disappears. So this means that now this function is a smooth function. So this means that the standard sampling technique of the Brillouin zone is enough to give an accurate value of this integral. And then we have to add it, but of course this is again a very diverging function, but now we have an analytic form for this, and we can, and this analytic form is such that we are able to analytically integrate this object. So what we can do, we have these two terms. This term is now a function that we know how to analytically integrate. It's just the integral of a Gaussian function, and this is the result. So it's something that, I mean, it's a number, and you can compute it easily. And now this blue term, it's a term that doesn't have anymore the divergency. So you can compute with the standard mesh of Q point. Still, there is some, you have to do it with some carefully, because still the limit of Q equal to 0 is not well defined in a calculation, because you have a 0 over 0 term that you cannot compute it explicitly. And this is done in quantum espresso, introducing an extrapolation technique. The assumption is that this integral, that is, let's say, a sum over Q and G vector, is done on a coarse grid of Q plus G. And then we also assume to have a dense grid of Q plus G point, and then we assume to have a coarse grid of G plus Q point in which we skip one point every two. So in this, we accurately sample the mesh. In this point, we have a less dense mesh. But what we, so this means that in the weight, so if you want, this integral is a sum over all your points in the grid divided, let's say, by the number of the points. So this means that here you have a number of points in the grid that is 8 times bigger than the number of points you have here, simply because you skip 1 point every 2 in each direction in this integral here. So this means that the prefactor, so the weight of your integral, it's just, there is a factor 1/8 in front. But then if you assume that these and these integral are already good enough, so if your grid is already good enough to give a good estimation of this integral, you can assume that these two quantities are already converged, even if you use a coarse grid. So if you assume this and you say that these two objects are identical, you can find an expression for this object. That is exactly what we miss in the term we would like to address in this calculation. So, and this is what is implemented in PW. And there is a flag to control this extrapolation that is called X gamma extrapolation that can be set to true or false, depending if you want to use this extrapolation scheme or not. And as you will learn in the afternoon session, this is very important. And you will find that using this extrapolation scheme and the Gigi Baldereschi, it's I mean, essential to have converged the result for the exchange energy. Oops. Well, maybe that I can skip because I'm really running late. So this is then what I was saying, that usually the hybrid functional calculations are really demanding in the sense that this is, let's say, the computational cost you need to, you have to compute the kinetic operator and the local potential. So this is, let's say, a standard LDA or DGA calculation, because I mean the kinetic operator is diagonal in G space. The local potential, you do it again with fast Fourier transform. You go in real space, you multiply the wave function, and you go back to G space. Then you may have a non-local pseudopotential, like what Raf Gebauer discussed yesterday. But also, usually also this is not a big deal. It can be easily done with fast Fourier. It's just number of plane wave times the number of projectors you have in your non-local pseudopotential. But the non-local artifact operator is something much more expensive to compute because you have this summation over Q point, an extra summation over Q point in the Brillouin zone, and a summation over the band. So depending on how accurate you want to compute this integral, you immediately realize that computing the artifact exchange is 10 to 100 times more expensive than a standard DFT calculation. So in order to reduce this workload, what one can do is, let's say, a downsampling of the Brillouin zone. Of course, this is a price of some accuracy in the calculation, and this is something that you already need to check. There are some parameters in the input file of PW, these NQX1, 2, and 3, that exactly specify the grid of Q point you want to use for the sampling of the Brillouin zone. And by default, they are set equal to the K point mesh you use in the standard DFT calculation. So you can reduce this number of Q points. So of course, this speed up the calculation, but you always have to check your convergency. So if you want, these are converging parameters. The other thing you can do, you can use smarter algorithm, like for instance the adaptive compressed exchange. Here you find the references. I will not discuss the algorithm in detail, but these save a lot of computational time, especially when you increase the size of your system. And this, I think, has been recently implemented in Quantum Espresso and has to be, in any case, activated with a compilation flag in your make file. I mean, this is just to make you aware of this. We are not going to use this in the exercise session. The other thing you can do is to use a range separated approach. I mean, the reason why the artifact energy needs a lot of Q point to converge is because you have a long range interaction. So you really need to have a big supercell, or if you want a huge number of Q point to accurately describe this long range interaction. So the idea is that if you neglect or somehow treat in a more efficient way this long range interaction, you can save some some computational time. And this is what is done, for instance, in this range separated hybrid function. The idea is to rewrite the Coulomb interaction in this form using some auxiliary function, the error function. And this is an exact expression, but now this first term is short range in the sense that it decays much faster than 1 over r when you increase r. And this is the long range part that decay like 1 over r for for big value of r, and is smooth for r that goes to 0. What in the Scuderia group, what they did realize is that so if you just replace the Coulomb operator, the Coulomb potential by this term, you are not doing anything because this is an exact identity. So it's just a way of rewriting it. But if you rewrite it like this and then realize that the non-local artifact and local DFT long range exchange, so this part, are usually small and tends to compensate one each other, what you can do, you can drop out this second term in the Coulomb kernel, so you have a much faster decay of the Coulomb interaction, and you can save some computational time in the sense that the mesh of Q point or the dimension of your supercell in the case of isolated system calculation the convergence is much faster. And this is another famous hybrid functional that is HSC 06. It's a kind of range separated hybrid function, so it's slightly different from what we saw so far. Okay, and this is how do they perform. These are again atomization energy of small molecule on a set of, big set of molecule. And again, here I compare this B3-leap and PB0 hybrid functional with LDA, PB, and B-leap that are okay, local density approximation to generalized gradient approximation. And here the value are in kilocal per mole, so the chemical accuracy is 1 kilocal per mole, and as you can see, okay, B-trip already do a great job, but if we go to hybrid function, we reduce by a factor 2. So this is the reason why chemists usually like this R3-Fock hybrid functional scheme. Another important, okay, for solid, again, I just give you a brief summary of lattice constant and bulk moduli of selected solid system. And again, PB compared to PB0, HSE, and B3-LEAP. And as you can see, the mean relative error goes down quite a lot if we pass from PB to hybrid functional. In this case, it's true for PB0 and HSE, but not from B3-LEAP that actually perform very well for atomic system. And here you have the bulk moduli. Again, here I highlighted the best function that seems to be PB0 for these, let's say, very small set of solid. And another important property is the, that actually I didn't discuss much, but is the well-known problem of the band gap of semiconductor insulator in DFT. So LDA and PB usually give an underestimation of the ionization of the fundamental gap, while if you resort to this kind of hybrid functional, mixing some R3-Fock with some local DFT, give you a much better agreement with experimental data. Also, for systems where LDA and PB where LDA and PB predict the system to be a metal, this hybrid scheme, gives instead a finite gap. So it's really a qualitatively improvement in this case. Especially HSE has a remarkably good performance for the gap. But this is, especially true for smaller, medium band gap system. While if you increase the band gap, the agreement is less impressive, let's say. And the reason is that, you may expect that the parameter you put in defining the mixture of R3-Fock and local exchange is something that should depend on the system and should depend also on the screening property of the system. So if you go toward metal, you would expect kind of more screening, so the R3-Fock fraction should be less than 0.25%. The opposite is true if you go to very wide gap insulator. So in principle, the mixing parameter should be also system dependent. You cannot expect to have only one parameter that works for all the system you are interested in. Okay, this is just a summary on hybrid functional. So they try to address the self-interaction and the delocalization error of DFT, more or less like DFT plus U tries to do. They give rise to systematic improvement over LDA and GGA. Actually, the energetic and structural property are usually better, especially for molecular insulator, less for metal in general. The band gap greatly improves. But on the other side, they are computationally much more expensive than LDA and PP and GGA. And as I was saying, the mixing parameter is not, it should be system dependent. You cannot use one parameter for, in principle, one parameter for all of them. Okay, and now I switch to another topic that are the van der Waals interaction in density functional theory. First, let me just give a brief introduction on van der Waals, what they are. Actually, they are dispersion forces. They are ubiquitous. They sum up. Even if they are very weak, they can sum up and give substantial contribution to interaction energy in biomolecule, but in general sparse matter, and they are also very important in adsorption of molecule on surfaces and in a lot of application. These dispersion forces are known since a long time ago, and they rise from the interaction of transient electric multiple in your system. And the leading term is, of course, the dipole-induced dipole interaction. And this is the term that gives the well-known r to the minus 6 dependence in simple dimer when you stretch the bond. And this is what I try to illustrate here with this cartoon. So suppose that we have two spherical atoms very far apart, separated by a distance that is much bigger than the atomic size, let's say. And suppose that at a certain point, by 0-point motion of this system, or by thermal fluctuation if they are relevant, we have instantaneous fluctuation of the charge density that induces a dipole, that generates an instantaneous dipole on this molecule. This, of course, generates a field, a dipole field that decay like r to the minus 3, and induce a dipole on the other atom. And usually this dipole, dB, is related to the polarizability, dipole polarizability of the atom B times the dipole field generated by this, the dipole on the atom A. And of course, then this dipole B interact with the electric field generated by this object. So the interaction energy is the product of this dipole times the electric field. And at the end, you have the well-known r to the minus 6 decay as a function of the interatomic distances. So this is now I just give a naive explanation for this, but this is a rigorous result that can be derived with second-order perturbation theory, where we use the Coulomb interaction between these two very separated objects as a perturbation. And this is a very general introduction, and then what we can say about van der Waals interaction. First of all, they are a pure correlation effect. Moreover, it's a non-local correlation effect, because as we see, charge fluctuation in a part of the system induce the response in a other part of the system very far away. And this means that since it's a correlation effect, it's not present at Hartree-Fock level, so hybrid functional does nothing with this kind of interaction. Moreover, it's non-local, so LDA and GGA being local in nature, they cannot address this kind of correlation. And this is again an example of again krypton dimer, as I already showed you at the beginning, so I will not go through again this. And you have a qualitatively wrong behavior for the dissociation energy. And here this is a more, let's say, real-world application. Here you have the DNA base pair, and depending on the configuration, the binding between these two molecules is, in this case, due to hydrogen bond. And if we compare PBE with some accurate reference, as you can see, PBE is not that bad. I mean, it's very good, actually, and predict we have a very good agreement with this reference calculation. But if we look at the very same system in another configuration, so it's a stacked configuration, in this case, the binding is mainly due to van der Waals interaction. So there is no charge overlap, let's say, in here. And as you can see, PBE perform really poorly in this case. So this means that you cannot trust PBE, for instance, if you want to address at the same time this kind of configuration. So how can we deal with van der Waals in density functional theory? So this is a quite recent, there are quite recent improvement in this, and there are very simple corrections starting from the very basic one. We completely disregard this effect, or even better, somehow better, we can use functional that are aware, in a sense, of van der Waals interaction, in the sense that they are fitted, they have some parameter inside, and they are fitted on a database that contain van der Waals molecule. Of course, this would give rather good results in, can give good results in van der Waals system, but only close to equilibrium, where they are, where the fit is supposed to be done. but we miss all these long-range interaction and very peculiar decaying like r to the power 6. The other approach that I will briefly discuss is the what is called DFT D, where D stands for dispersion. And in this case, what people do, as I will show you in the next slide, is just add a corrective term to the total LDA or GGA energy that takes into account this decay as a function of the density. But then there are also truly functional development that depends on the charge density of the system, but in a non-local fashion, in a way, and they are really, DFT functional and are really non-local functional. And the most maybe famous one are van der Waals density functional is revision, let's say, DF2, and the VV10 function. And then I will, if I have time, I will just say something also about random phase approximation and something beyond random phase approximation and how do they perform for van der Waals system. But just let me start with this simple correction. So the idea is that we know that at least for this spherical atom far apart, we need to have a r to the minus 6 interaction. So what we can do is that we can write our energy as a DFT energy, LDA, GGA, or whatever, plus what is called a dispersion contribution that is usually written as a sum over term like one of the form 1 over r to the power 6. So what you are doing is that you are taking your system, and for all pair in your system you add this kind of correction, where this is a coefficient that depends on the pair of atoms that you are looking at. And this is the general expression. Here you have a global scaling factor that usually is fitted on, again, on a set of reference molecule or system. And it depends on the, of course, on the choice you made for this density functional theory. So if you have LDA, this has a value. If you have a PBA, this has another value, and whatever. Then let me focus on this term. I say it's a pairwise additive term. But how to define this C6 dispersion coefficient? I mean, there are different schemes, from very simple one in which you take this value from experimental data set. More refined one, like the one I describe here, it's what is called DFT minus D2, where the C6 coefficient for any pair of atom I and j is written as a geometric average of the C6 coefficient for isolated atom, and each of these C6 coefficient of isolated atom is taken from the London dispersion formula, and is proportional to the ionization energy of the atom and its polarizability. Then this value I of I and alpha of I are tabulated for a lot of, almost all elements. And then during the calculation, you take any pair of atoms in your system, you read this tabulated value, and you compute this C6 coefficient. Of course, I mean, this is an approximation because this C6 coefficient, in principle, should depend on the environment. I mean, if you have a pair of atoms in a given system, then the C6 coefficient has a certain value. If you embedded the very same pair of atoms in another system, you may expect this to change. And of course, this is not taken into account in this very simple scheme. So what is missing is the information on the chemical environment. And the other, let's say, almost empirical parameter you have is a damping function that prevents the divergence of this term when r goes to 0. And also this, it's a very important and tricky part, because you have to choose this parameter d and these radii, again, in the right way to balance the DFT energy and the dispersion energy. So when the dispersion take over the DFT, so it's a very tricky part, and it's in the literature you have a lot of discussion on how to define these damping functions. So this is just to say that you have a lot of empiricism in here. You can do somehow better introducing the chemical environment, somehow taking into account the neighborhood of your reference atom. So there are different ways of taking this into account, and this leads to different scheme, DFT minus D3, van der Waals, Tachenko-Scheffler, and some refined method that I will not discuss here. But this is just to say that you can somehow take into account the dependence of your C6 parameter on the chemical environment, looking at some, if you want geometrical property of your atom in the system. So for instance, in what is done in the Tachenko-Scheffler, they take the reference C6 coefficient for a free atom, and they scale down using the ratio between the volume of the atom in the system and the volume of the atom in the gas phase, if you want. So they have a way to compute this object, partitioning the density in the system. And the idea, rationale behind this is that if you have if your atom is compressed or squeezed, this means that it's less polarizable, and so what you end up with a C6 coefficient and a polarizability that is scaled down by this compression factor, the ratio between the actual volume of your atom in the system divided by the volume of your free atom. And this is just to say that, I mean, there are a lot on the literature, and you can find detail here. But what I want to discuss more in detail are these truly non-local functional that are really DFT functional, and they usually look like this. You have this non-local correlation function that is an integral of, in 2 points of the space R and R prime, of the density in R and the density in R prime with some kernel function that now I will show you how is defined and which property it has to satisfy. This was, I mean, the breakthrough, I think, was this paper in 2006 by Dion and co-worker, where they were really able to define in a physical meaning object phi of R prime, and this is the breakthrough paper, and then followed by some other refinement, and then different form of non-local function has been derived depending on the choice of this kernel function phi of R prime. Also, RPA functional can deal with van der Waals interaction, and this is a review if you want to look in detail on the RPA. But what this scheme, RPA and true non-local function, has in common, it's again that they can be viewed as an approximation, or they can be derived again from the adiabatic connection formula with some additional information, that is the dissipation fluctuation dissipation theorem. So just let me again go back to this adiabatic coupling. This is exactly what we saw in the very first slide of the talk. We write the interaction energy in terms of this 2-point correlation function. But now we add this extra piece of information. Let's say the fluctuation dissipation theorem tells us that we can rewrite these objects that are the density-density correlation function, so that describe density fluctuation in your system, can be related to the energy dissipation of your system. That's a very well-known theorem of statistical mechanics. And the dissipation of the energy is, as you know, related to the imaginary part of the response function. So at the end of this story, at t equal to 0, you can write this object as an integral of the density-density response function. If you substitute, you end up with this exact expression of the exchange correlation energy in terms of the density-density response function. So it seems we are increasing the complexity of the discussion, but what one can do now is that use some intuition on the density-density response function. But first of all, I want to just highlight that if you just take the lambda equal to 0 term, so if you replace chi lambda with chi naught, So if you take only lambda equal to 0, you can work out, and you again recover what we saw in the previous slide, that the term at lambda equal to 0 is nothing but the exchange energy. And what is left outside, so if you add and subtract this exchange energy, is only the correlation energy that comes out to depend only on the density-density response function for the system at interacting strength lambda and for the non-interacting system. So this is the Cohen-Sham response function, and this is the, in general, unknown response function for the interacting system. So now the problem is reduced on find the approximation for the response function. So I will try to show you how to doing some approximation on the response function and on this exact expression for the correlation energy leads to a form like this that is actually exactly the non-local van der Waals function I was introducing before. But you can do even something more, of course, computationally expensive, but more ab initio in a way. So you can really solve what is called the Dyson equation for the response function, that is, let's say, an exact expression for the chi of lambda in terms of the Cohen-Sham non-interacting response function and the exchange and correlation kernel. And from the approximation of this Dyson equation, you can find what, it's a very straightforward way to derive the random phase approximation or some other more refined approximation. But let me start with some comment on this formula. So what I want to point here, I don't want to go through all the detail that you can find in very nice paper here and some review, so more general review on this van der Waals in DFT. But what I want to point here is that given this exact expression, you can really find what we were discussing before, the dependence 1 over r to the power 6, just going through a sequence of approximation that I just try to sketch here with this. First, you assume some RPA dependence on the response function, and this means that you can integrate analytically over lambda, and this simplified this expression. Then what you can do is to assume that you have a separate fragment in your system, and this is a very big assumption, so you are really restricting now the system you are looking at, and made by two well-separated fragments. So you can write the response function as a sum of the two response functions in the fragment A and B, plus some correction. And then if you expand to second order in the interaction between these two fragments, you can eventually even more simplify this expression, and you end up with something like this, where you have the only ingredient you have now are the response function of the system, the subsystem A and subsystem B. You can introduce the polarizability tensor, so that is related to the polarizability we saw in the previous slide. If you do another approximation that is a local and isotropic approximation for this tensor, that actually depend on the direction I and j, r and r prime, you make it local and isotropic. At the end of all these approximations, you end up with a second order correction of your energy that has a very close form to the one that we saw at the beginning. So if you assume now that the fragment A and B are very far apart one to each other, you can take out this denominator from the integral. This gives you the well-known r to the power 6 behavior, and this gives the C6 coefficient as an integral over the polarizability. So this is just to say that if you have some physical intuition on how to treat this object and how to simplify this expression, you are able really to recover what you know from experiment or from other simplified picture. But this is not the end of the story, because in principle, in order to calculate this object, you need to calculate this polarizability, and these are quantities that are hard to compute. You can compute it, but with time-dependent density functional theory, for instance, so very refined method. What we can do now is to go further with another approximation and find some approximation for this polarizability in terms of quantity that we know how to compute. So what I want to do now is to write an approximation for this polarizability in terms of the density or eventually gradient density or gradient of the density in my system. So, and this is usually done taking some simple model. It actually comes from the fact that, so if we take the average of the polarizability over the whole space, we have something that is physically observable, which is the polarizability of the system as a function of the frequency. Okay, here I'm working at imaginary frequency, but just for convenience. And we know that this observable has to satisfy some rule. For instance, in the limit for imaginary frequency that goes to infinity, this has to go down like 1 over u square, and with the prefactor that is related to the number of electrons you have in your system. So with these two pieces of information, what people usually do is to use a very simple model of the local polarizability, and it's a kind of plasmon-pole mode, because you see here there is a characteristic frequency of your system, omega 0, and this is it's like you are assuming that your polarizability at point R has a characteristic frequency omega 0, and then these expressions satisfy these two conditions that I brought down here. So this is again an approximation for another approximation, and if you now plug these into this expression, you end up with we are almost there. So you find that this is a kind of n of r, nr prime, then you have some kernel function, and r minus r prime to the power 6. That looks like what you want to have for separated fragment in your system. But of course, here, I mean, from the very beginning, we start with the approximation that we have separate fragment in our system. This is not always the case. If we have, let's say, a complex system, we cannot really imagine it as made by non-overlapping fragments. So this is a very crude approximation, and indeed it works, I mean, only in some special case where you have well separated atom or molecule. What is done in this paper that I was saying it's the real breakthrough is that they release this assumption of having well separated fragment in your system, and they find a general expression for this kernel function that can be applied to system with general geometries. So you don't have to care anymore if you really have separated fragment or you have overlapping fragment. This is a general function to deal with general geometry. So what is done in this paper is that, again, they write your correlation energy as the local density approximation plus this non-local correlation energy, and this non-local correlation energy is essentially defined by this kernel that depends on the density in R and R prime and on the variation and the gradient density. And what is important is that when you take the limit for R minus R prime that goes to infinity, you recover this model that we derived for the isolated fragment limit. So this is a necessary condition this kernel function has to satisfied. And then again, you are only left on how to define this characteristic frequency that enters in the expression of your kernel. And of course, if we want to have a function of the density, we should be able to approximate this characteristic frequency as a function of the density. And this is usually done usually taking some, like it's done in LDA for the correlation energy, this can be done also for the characteristic frequency, taking some information from the homogeneous electron gas. But at the end of the story, what happens is that these omega 0 only depend on the density and the gradient density. So your functional here really depends only on R, on the density in R, R prime, and the gradient density. So this is really a functional of your density. And then, of course, a different model of the omega 0 really define your kernel. And this I just put these table here. I don't want to go into detail, but just to say that there are different forms of these model, this characteristic frequency omega 0 that depends on the density and the gradient of the density. I mean, this is the local, oops, I know. This is the local, yeah, I was saying, all these non-local functional, I mean, has some definition for the characteristic frequency that actually then define your kernel phi of R. And inside here you have the local Fermi wave vector. You have the S that we saw at the beginning is the scale gradient of the density, and you have LDA correlation energy, for instance, or maybe not. Or the plasma frequency, the local plasma frequency that is a characteristic of the homogeneous electron gas just computed at the local density in your system. What I also want to point out is that, I mean, which exchange and correlation we have to use in combination with this non-local correlation energy. I mean, there is a lot of literature discussing on which exchange and which generalized gradient correction for the exchange to use in combination with the non-local function. Essentially because somehow this LDA and generalized exchange already give a spurious binding, why they shouldn't, for example, in van der Waals dimer. So it's really a delicate issue how to combine exchange with this kind of correlation, non-local correlation. So here I just write for clarity which, so this is the LDA exchange later, this is the Perdue-Wang correlation, and this is RPB is the exchange gradient correction. Here instead we have a different exchange gradient correction, here we have the same as here, and here again we have, here we also have a different correlation energy, is no more the LDA energy correlation energy, but is the PB correlation energy, so with the gradient expansion. Okay, how do they perform? Here I just put some benchmark on a set of molecules again, and here you can see that here I just plot the binding energy with respect to very accurate quantum chemistry calculation for non-covalent bond system that are in this. This is a set of 22 molecules that have this kind of hydrogen bond molecule, van der Waals interaction, or mixed hydrogen bond and dispersive interaction. All these, I mean, vdV, DF, VV10 that are truly non-local functional, or also the DFT plus dispersion correction, they work pretty well, and they give mean relative error, I mean, close to 1% in the best case. So they really do a nice job. Here there is the argon dimer. The black one is the reference experiment, and you can see this BB10 functional. I mean, it's really performing well. Still, some of the other, the VDF is not really giving a good performances, but its revision really slightly improved. So this to say that this has to be used with some caveat. It's not a panacea, let's say. You have to always test and be sure that these are really working and doing what you're supposed to, you want to see. And this is also the lattice constant and Mach moduli again for selected solid, because what we want is that this RVV10 is not going to spoil the good performance of PBE or LDA for lattice constant, and this is actually what happened. This BV10 function is not going to change more the lattice constant or bulk moduli that we had at PBE level that are already very, very good. So what time am I supposed to stop? Now, maybe. It's done? Yeah. Okay, so sorry, I will skip this RPA and RPAX, even though actually it's what I worked mostly on recently. And I just try to give you a summary of, what the message I wanted to convey is that LDA and it's simple and well-defined. It's a well-established approximation. We know a lot on it, why it works, why it fails. Usually gives good geometry, but tends to overbind. GGA correction improves on the energetics, give good geometry, sometimes overcorrect LDA. Hybrid functional tends to address the self-interaction error, but with some limitation, of course. We saw that this mixing parameter is system-dependent. We cannot expect to have one for all of them. Van der Waals functional, it's a very active field, so a lot of development is going on this field, and they usually work very good, and nowadays, the computational cost is more or less like LDA or GGA calculation. And unfortunately, I skipped this RPA part, so this is the end, and I thank you for the attention.